So I'm Skylar. I'm a .NET developer by day, but I've been playing about with some audio programming in my spare time. Just a bit of background, so you know that I'm not some sort of expert on this. Um, I'm familiar with synths. I've been playing about with synthesizers for quite a while, making music with them, but never sort of jumped into developing them. Not used C++ for a lot of this, and I've been perplexed by it for years, and not really done much by beyond Hello World until a few months ago, when I sort of picked this project up. So the main question is, what is a synthesizer? Synthesizers are machines that produce sound electronically. So they'll generate sounds. You may have heard them on. I'll just do a quick demo and show you what we're going to be building up here. So let's move on to the screen. So it allows you to electronically produce sound. So it plays as an instrument. So I'm currently playing in a little sequence, and then you can tweak that sound and make it sound very different. That little excerpt was definitely not stolen from Stranger Things. So what we're using for this is a library called Juice, which will handle all of the UI elements and the communication with the audio hardware. So what's quite nice about that is I've been able to work on this both on Windows and Linux, and it's just handled all of the sort of audio drivers for me. And I'm also using a library called Daisy SP for the actual audio processing element. So audio signals. So sound. You might already be familiar with the idea that sound is vibrations that your ears pick up, and we can represent that as a wave. So this is how the sort of pressure that represents the pressure changes essentially on a graph. And as part of that, you have this concept of wavelength or frequency, and this is generally how fast the wave repeats. And what that translates to is pitch. So a higher frequency will result in a higher pitch. So that's usually measured in hertz, which is the number of repeats per second. In terms of moving that into the digital world, with the audio signal being analog, we have to kind of make some concessions when we convert it into a digital signal. So we chop up this time into, we kind of select, find out what the amplitude of the wave is at any given time, and each of these is a sample. So we would say this here would be 0, and you'd have +1 or -1 or some sort of similar scale to that. And then you just sample at each of these points. I guess the first concept really is to cover is an oscillator. This is what produces your initial signal. So there are different wave shapes. So the oscillator produces a constant signal, and there are different wave shapes to this that affect the sound. So these are the basic waveforms here. You start with the sine, which is quite a soft sounding wave. So I'll just second. Sorry about that. So you've got the sine, which is quite a soft sounding wave. It's got very little in high frequency content. It's probably the purest. And then you get slightly harsher with the triangle wave. It's still quite soft. And then you move into the saw wave, which is significantly harsher. And then brace yourselves for the square, which is the most aggressive of the sort of basic waveforms. A good rule of thumb is that the more angular the shape of the wave is, the more aggressive the sound is going to be. So what this looks like in code, thanks to Daisy SP's simple interface, is we have an oscillator class and we just run process for each of those sort of sample points on the wave. So we get out of that simple float, and then all we're doing with this here is timesing it by a number between 0 and 1 to sort of change the volume of that. And then we can also set the waveform. Excuse the number of if statements here. This is just for illustration. But yeah, we can change to each of those waveforms. And we can also set the frequency or the pitch of this. So each time we press a note, it will convert it to a frequency in hertz, and then set that frequency. And then it would be quite boring if all we had was that. So we have this ability. We have the ability to fade in a second wave. So we can include a second wave, and we can change the pitch of that. And we can also introduce noise, which is like a windy kind of sound. So to mix signals like this, because we're working with a single sample at a time, we can mix these together just by adding together the value that we get out of the oscillator for each of these. So we can add them together, and then we just divide by 3, so we're not increasing the overall volume by 3 times. The next concept is the idea of a filter. So a filter can shape this initial waveform. We have, in this example, we're using a low-pass filter, which is one of the most common filters that you'll find on synths. And low-pass filters essentially remove some of those high frequencies, so they can make the sound sound a lot softer. So that would sound, I can play you a filter being out and cutting off some of the sound. So it can cut out the sound until it's completely gone, because we've cut out all the frequencies that we're producing. And then we have this concept of resonance, which is at the point that it's cutting off the frequencies, we can emphasize that point, and that can sound almost laser-like. So let's turn up the resonance and do our filter sweep again. You might sort of recognize that sound if you're into acid sort of techno. The code for the filter is really nice with Daisy SP. Because we're affecting a signal that already exists, the only real difference from the oscillator is we pass in the sample that we've already sort of processed for the initial wave. And now we come to the concept of an envelope. So sounds would be boring if they didn't change over time. So envelopes we can use to change a note across the sort of across time, and it's almost like an invisible hand moving a control. We can use it to change the volume, and in this example as well, we're using it to change the filter. So there are 4 distinct phases to a filter generally. You have the attack, which is how long it takes for the sound to fade in. So in this example, turn that down. In this example, it would be instant. So, but then we can also increase that time, so it kind of fades in, and you get like a softer sort of sound, less sort of sudden. Then there's the decay phase, which is while you're holding the note, how long will it take to reach another level, which is the sustain. So as you can see, I'll show you here. I've got here. There's a longer decay here, and then we can shorten that. That'll be a really sort of short, snappy note. And then the next phase is a sustain. So as you could hear then, in the previous example, the sustain was at 0. This is the level that that the synth will go to while you're holding the note. So what's nice about synthesizers compared to something like a piano is that the note can last forever. As long as you can hold the button, the note can go on. So in this example, we've got a sustain level, and then so I'm holding the note, and then I let go, and then we enter the final stage, which is the release. So this is how long it takes to die off after you've let go of the note. So you've heard what a short release sounds like, where there's a sudden stop, and then you'll have like a slower release, much in the same way that if you let go of a piano key, it won't instantly deaden the sound. So the code for the amp envelope is or the volume envelope is very simple. All you need to do is change the signal volume. I've just realized this code's out of date. All you would so what you do here is you get the value for the current envelope value, and this gate open variable here is whether the key is pressed or not. It needs to know that because so that it can determine whether to be in the decay stage or the release stage. And then all you do here is change the volume of your main signal based on that value. This is slightly outdated. This is using a multiplication in the actual code. And then you have the filter envelope, which you heard in the kind of intro, which is the movement of the filter over time. So I'll just do a bit more of an extreme example so you can hear it. So that's, you can hear that. We can move the filter, and then we can have that release and do its thing. It's a little bit more complicated than the amp envelope. You first get the current state of the filter, of the envelope. So we pass in the note, whether the note's on again. Then we have to set the frequency of the filter. So we're sort of setting that point where it starts to cut off the high frequencies. And then we're sort of doing our processing code again. And then I guess this section is mistakes that I've made with this, and things to learn from, and just general improvements. One sort of the teething pains from touching C++, which are all of the build issues I've encountered, but one of the main sort of gotchas that I've noticed a lot once you've got the build set up is when you add new files, you need to add them to the sort of build manifest, I guess, which is something I'm not used to being mainly working in .NET before. In this project, there's a lot of code duplication and boilerplate code. Some of that was on purpose to sort of reduce the complexity. There's definitely ways to fix that, but I didn't put too much thought, just so not to over-engineer for demonstration purposes. And the biggest lesson I learned was add a volume control first. When I first started playing about with the library, I almost blew my ears out with an extremely loud and harsh sound. So I recommend putting a volume control in there first. You can find the code on my GitHub. I'll post that in a comment to the meetup group so everyone can see that if you want to poke around. And that's it really. Is anyone got any questions?